BYD has created an electric vehicle without a battery pack. They didn't shrink it down, and they didn't hide it somewhere clever. There is simply no separate battery box at all, because the vehicle's actual frame is the battery. Every single floor panel and load-bearing section of the car holds everything together while simultaneously storing energy. And during their March 2025 presentation, one specific number completely stunned the audience. The car charges from 10 to 70% in just 5 minutes. You heard that correctly. 5 minutes. That is quicker than a fast trip into a gas station convenience store, and it yields roughly 250 miles of driving range. However, this insane charging speed isn't actually the biggest breakthrough here. It is only the beginning, because the exact same structural architecture that enables a 5-minute charge also makes the entire vehicle significantly stronger, noticeably lighter, and far more efficient, all at the exact same time. Give this video a quick like and hit subscribe so you don't miss our future deep dives. By the time this video ends, you will fully grasp why this specific engineering leap, not the extended range or the charging rate, is what forever changes how electric vehicles will be built from the ground up. To really understand why this matters, we have to look back at the technology it is replacing. The traditional electric vehicle battery pack stands as a brilliant piece of engineering from the past 3 decades, and it genuinely deserves our respect before we start criticizing it. Automakers didn't just stumble upon the giant flat-floor battery by chance. They created it to answer a truly difficult challenge. How exactly do you pack in enough power to drive a 4,000-pound machine for hundreds of miles, safeguard it during a massive collision, shield it from extreme heat, freezing cold, and deep puddles, and still keep the price tag reasonable enough for someone to actually buy it? Their solution was modularity. You start with small individual battery cells, whether they are cylindrical or rectangular, that each hold a modest amount of power, and you bundle them together into modules. Then, you pack those modules into a massive, flat tray. You wrap that tray in a tough, armored shell, bolt it underneath the cabin floor, and design the rest of the automobile around it. Keeping this heavy box low to the ground lowers the center of gravity, which makes the car handle incredibly well. It also keeps all that heavy mass far away from the front and rear crush zones, greatly improving passenger safety in a crash. Engineers absolutely adore this setup because of its flexibility. You can easily adjust the size of the battery for different ranges without having to engineer a brand new car chassis. Manufacturers love it because the assembly process is deeply entrenched. Suppliers make the cells, a different factory builds the modules, and the finished boxes are shipped straight to the main assembly plant. Regulators are huge fans too, because it's easy to evaluate. A separate battery box can be independently safety tested using rules that already cleanly exist. Yet, there is one obvious question almost nobody bothered to ask. Despite how elegant this design was, why did no one ever seriously challenge the rule that the car's body and its battery had to be 2 completely distinct items? It seems like an incredibly naive question when you say it out loud today. Why wasn't this challenged years ago? The honest truth is that the auto industry evolved entirely around gas-powered engines, where the fuel tank is always a distinct object. It's a metal tub that holds liquid, bolts onto the frame somewhere, and feeds the motor through a pipe. Early electric vehicle engineers completely adopted that old mental model without second thought. The battery was treated as a container, a discrete box you mount inside a car and build around. That philosophy stuck around for decades because the engineering trade-offs at the time actually supported it. When battery tech was in its infancy and safety rules were still being drafted, having a replaceable, easily testable box was the logical move. The old way wasn't defective. It was completely rational. The only real question was if it was still the absolute best way to build a car, and the answer revealed a deeply buried flaw that most folks preferred to ignore. The traditional standard was clever, but what it was hiding was something else entirely. The underlying problem with the modular battery isn't some spectacular, dramatic hazard. It is a silent, snowballing waste of space and weight that only gets worse when you try to push the car's performance. It all traces back to a statistic that seems completely boring until you actually do the math. Inside a traditional electric vehicle battery pack, roughly 40 to 50% of the volume inside isn't even battery cells. It is everything else. It's the outer armor, the thick structural foam, the cooling pipes weaving between modules, the massive wiring cables, the thermal shields, and the heavy metal brackets keeping everything locked down inside the shell. None of this is structural framing for the car. None of it holds energy. It is pure packaging, and packaging alone. Imagine packing up to move houses. You fill a box carefully, but by the time you add all the bubble wrap, the cardboard dividers, and the heavy padding for fragile corners, your actual belongings only take up about half the space. The box is doing its job keeping your stuff safe, but half of what you are carrying around is just dead weight. A normal EV battery functions the exact same way. You are dragging around a massive amount of engineered wrapping paper, and that wrapping paper serves only one single purpose. This isn't just about one wasteful part. It is a fundamental design limitation that forces every other system in the automobile to make compromises. These packs are heavy. A normal battery in a standard sedan weighs about 1,000 pounds, roughly the weight of a grand piano. Yet, the car's frame has to be beefed up to carry all that dead weight, without getting any structural support back from the battery itself. You absorb the full weight penalty without getting any stiffness benefits. This triggers a terrible chain reaction. A heavier battery requires a tougher, heavier floor to carry it. A heavier car needs more juice to accelerate and stay at highway speeds. Needing more energy means you have to build an even bigger battery. A bigger battery adds even more weight. This cycle keeps feeding itself, dragging the vehicle further and further away from true efficiency. Engineers have a specific name for this nightmare: parasitic mass growth. Every extra pound added to manage the battery requires roughly 3 additional pounds elsewhere in the car just to support it. When you scale that up to a full battery pack, the penalty adds up fast. Then you have to deal with the heat. All that extra packaging needs cooling tubes snaking through it to stop the battery cells from cooking themselves during rapid charging. The more intricate you make this cooling grid, the more weight you add, and the more potential leak points you create. Back in 2021, BYD's engineering team began tackling this challenge with data that the rest of the auto industry simply couldn't ignore. The people who designed this new cell-to-body layout weren't some rogue secret group. It was BYD's Advanced Battery Development Lab, the exact same group that created their famous Blade battery. They teamed up closely with the Vehicle Chassis Design Division under a project they called the Integrated Energy Structure Initiative. The ultimate concept sounds incredibly basic when you think about it. What if the top surface of the actual battery cells doubled as the physical floor of the car's cabin? Not figuratively, quite literally, a load-bearing floor. Past attempts at building structural batteries always hit a brick wall. Usually, engineers would try to glue cells onto a chassis frame, but gluing creates intense stress points. You are essentially pasting together two different materials that expand and contract at completely different rates when hot or cold, and then expecting them to endure decades of road vibrations, changing weather, and heavy physical loads. When the temperature changes wildly, the glue wears out, the joints crack, and the cells start to shift. While Western research labs had built experimental structural batteries that worked in brief tests, none of them could survive the 100,000-mile durability standards required for actual production cars. This highlights exactly what those earlier projects got completely wrong. They kept trying to connect a battery to a car frame. BYD's team flipped that entire philosophy upside down. Instead of trying to attach cells to a separate frame, they just threw away the separate frame entirely. Think of a honeycomb sheet, like the ones used inside airplane walls. A single tiny aluminum cell is incredibly fragile on its own, but when you sandwich thousands of them together, the geometry spreads the physical load across all those walls at once, making the whole panel incredibly tough. BYD took that exact structural principle and applied it to their long blade cells. These cells are long, flat, and slender. When packed tightly side by side with their top faces perfectly aligned, They create a solid, continuous surface, just like a hardwood floor. A single piece of wood bends easily, but lock them tightly edge to edge across a room, and you suddenly have a foundation sturdy enough to support an entire building. Even better, the cooling tubes stopped being dead packaging weight. They were turned into structural support. Since the batteries can't just sit there unprotected, they still need to stay cool. BYD solved this by baking the cooling paths right into the aluminum frames that reinforce the car's floor from side to side. Every single ounce of metal now serves two purposes. It stores electricity, and it physically holds up the car. This isn't just a minor tweak to existing technology. It is an entirely new category of engineering. The big test was seeing how this radical design would actually translate into real-world performance metrics once on the road. Before we look at what this new setup can actually achieve, we should talk honestly about its downsides, because the real truth is a lot more compelling than a perfect sales pitch. This fully integrated approach makes replacing a single faulty cell much tougher than fixing an old-school modular pack. With a standard battery, a mechanic can just pull out one bad module without messing with the rest of the car. But in a cell-to-body vehicle, those cells are physically part of the frame. Reaching them means tearing apart sections of the floor. That inevitably bumps up long-term repair bills, which is something you really have to consider if you plan on keeping your vehicle for 15 years. But let's look at how this plays out in real life. Most EV battery wear happens slowly and evenly across the entire pack over many years, rather than a single, sudden module failure that forces an urgent fix. Independent tests on lithium iron phosphate cells, the exact chemistry BYD relies on, show they routinely keep over 80% of their original capacity, even after 200,000 miles of driving. So for the average driver, the headache of fixing a single cell is mostly a theoretical issue, not something you'll likely face during regular ownership. Where this setup wins without question is structural rigidity. BYD's internal tests, verified against standard industry twist and flex metrics, prove this platform is around 70% stiffer than their older cars with separate battery packs. 70%. That matches the stiffness of high-end supercars made from carbon fiber, which usually come with a $300,000 price tag. Yet BYD hit those crazy metrics without using space-age materials. They did it entirely with smart layout design. By using that honeycomb, load-sharing technique, the floor acts as one solid unit instead of a heavy box hanging under a separate chassis. This isn't just a minor battery upgrade or a tweak to the chemistry. It's a total reimagining of what a car floor can actually do. One unexpected area where this tech is already winning right now is winter shipping. Electric delivery trucks running in freezing places like northern Canada or Scandinavia have always faced massive drop-offs in winter range because the car has to waste precious battery juice just to keep itself warm enough to work. This integrated design maintains temperatures far more efficiently because the surrounding frame is the actual heating grid. There's zero empty space between the heat source and the battery cells. At this stage, nobody was questioning whether this tech worked. The real question was how fast it would spread. The very first consumer car built with this platform was the Han L sedan, which hit Chinese roads in mid-2024. Real-world data gathered from those cars over their first 6 months completely backed up what the lab tests promised. Even after racking up 30,000 miles of intense highway and city driving, the frame's stiffness stayed within 2% of brand-new factory specs. Real-world driving ranges averaged around 580 kilometers, or roughly 360 miles, matching official ratings within a razor-thin 4% margin. The real world perfectly matched the predictions. Why is that such a big deal? Because lab test results in the car world are famously over-optimistic. A clean, controlled laboratory can't replicate the brutal freeze of a harsh winter, the jarring potholes of city streets, or the heavy strain of a packed car cruising at highway speeds for hours. When real-world data from thousands of actual drivers lines up perfectly with lab models, you know the engineering is truly durable, not just a gimmick that looks good on paper. The most critical piece of the puzzle was how they built it. BYD didn't build massive new factories. They modified their existing production lines instead. They actually borrowed the aluminum pressing techniques for the integrated cooling frames from aerospace tools already used in the high-speed rail sector. This kept setup costs incredibly low compared to building a factory from scratch. A senior engineer working on the project pointed out that the real victory wasn't just the stiffness numbers, but the fact that those numbers stayed identical regardless of which factory or shift built the car. It proved the method was ready for massive factory production, not just handcrafted for a handful of show models. All this real-world performance data is publicly tracked in safety databases, updating every quarter. If you think combining a car frame with a battery is wild, what comes next is even harder to believe. Hit that subscribe button right now so you don't miss it. What started as a specialized project, where saving weight was more important than easy repairs, quickly exploded across the entire automotive industry. And BYD has the hard proof to back it up. Today, over 300 international patent families point directly to BYD's structural battery designs as the foundation. These aren't just boring academic papers either. These are massive legal and financial bets. Global automakers are spending fortunes on lawyers, filing fees, and development hours just to protect their own ideas around this technology, because they know this is where the future of car manufacturing will be won or lost. Where these patents are being filed tells you everything you need to know. The biggest clusters are in Germany, Japan, South Korea, and the United States, the exact 4 nations with the most to lose if this new architecture becomes the global standard. When your biggest rivals start filing defensive patents around your technology, it is the ultimate proof that you've built something genuinely revolutionary. Don't mistake the industry's response for mild curiosity. It's an all-out engineering mobilization. The Volkswagen Group poured roughly €2 billion into a dedicated structural battery research program running through 2027, using this exact cell-to-body layout as their baseline blueprint. Toyota's advanced research team filed over 40 patents in 2024, tracking the exact 2 problems BYD already solved: structural gluing and built-in heat management. Panasonic quickly teamed up with a European chassis maker to develop integrated cell designs, and CATL launched their own version called Free Voy, specifically to fight back. The real fuel driving this transition in Europe is an upcoming Euro NCAP safety rule change in 2026. It adds strict new tests for side impact cabin safety, a test where these integrated honeycomb battery floors absolutely dominate because of their natural strength. This single rule change transforms the cell-to-body design from a neat efficiency trick into a must-have safety shield. In a world where crash ratings heavily drive sales, a 70% stiffness advantage isn't just a passing trend. It's a brutal competitive force that no mainstream brand can ignore for long. All of this performance data has been thoroughly vetted by independent experts at universities in Shanghai and Munich. Looking ahead, BYD plans to use this platform for over 40% of its entire vehicle lineup by 2027. Given their massive scale of 4 million cars a year, that means over 1.5 million structural battery vehicles hitting the streets every single year from just one company. 1.5 million. To put that in perspective, that's roughly equal to every single new car sold in Australia in a whole year. There is another massive perk that gets overlooked next to the performance numbers: raw material savings. By completely eliminating the extra inner boxes, heavy outer casings, and thick layers of structural foam, the amount of steel and aluminum needed for each car drops drastically. Early environmental assessments show a savings of up to 200 pounds of metal per vehicle. When you multiply that across 1.5 million cars, you are saving up to 150,000 metric tons of steel and aluminum every single year. That is raw material that never has to be mined, manufactured, shipped, or eventually recycled. But turning a breakthrough technology into a global industry standard is a long, steep road, and we have to be completely realistic about where this path gets incredibly tough. The biggest immediate roadblock is the auto repair world. Less than 3% of independent mechanics worldwide have the special tools or training required to fix an integrated structural battery system. That figure has to grow 10 times over before drivers can confidently own these cars outside of major cities with official dealership networks. On top of that, insurance companies haven't figured out how to price the risk of frame battery damage in minor fender benders. Because they lack reliable data on what repairs will actually cost, insurers in many regions are adding extra fees just to protect themselves. This noticeably drives up ownership costs, wiping out a good chunk of the money you save on efficiency. Recycling these integrated setups is another massive challenge that's still in its infancy. Old-school battery recycling can easily detach individual cells from the support frames, but these fused cell-to-body systems require completely different recycling methods, and the factory capacity to handle them at a large scale barely exists outside of China right now. Then there's the raw material supply chain. Even though lithium iron phosphate batteries don't rely on rare metals like cobalt or nickel, the actual processing of raw lithium is still highly concentrated. The two largest lithium processing facilities feeding this supply chain are both located in a single province, roughly the size of Texas. Moving that processing power to other parts of the world will take years of heavy building, not just a simple stroke of a pen. Here is the one detail almost every analysis completely overlooks: standardization. If we want this structural technology to sweep across different car companies, the auto industry needs unified rules for dimensions and connections. Just like USB ports, standardized cords for thousands of different tech brands. As of right now, those standards don't exist, and the current patent war makes reaching a neutral agreement politically messy. The International Electrotechnical Commission does have a team working on it, but don't expect any official guidelines until at least 2028. None of these roadblocks change the underlying science. They simply highlight the massive bridge between what can be done in a lab and what will actually hit the streets. Crossing that bridge is a challenge for money, politics, and cooperation just as much as it is an engineering puzzle. The innovators who built this handed us an incredible tool. Whether the world actually uses it at the pace our energy transition demands is another story. Ultimately, the shift toward cell-to-body technology is about what we can build and exactly where we can build it. Every single historic breakthrough in how vehicles move has expanded human boundaries, allowing us to live in new regions, commute further for work, and connect remote towns to major hubs. This leap is no different, except it arrives at a time when the stakes for cleaning up our transport have never been higher. It's easy to miss the real economic impact if we only focus on high-end luxury sedans. The places that stand to benefit the most from affordable, long-range EVs aren't rich Western cities packed with charging points. They are growing hubs across Southeast Asia, Sub-Saharan Africa, and South Asia. These are places where food and medicine spoil because transport trucks can't safely navigate rural routes, where city smog is suffocating due to aging gas engines, and where the daily cost of transit eats up a huge chunk of family paychecks. The exact same weight savings that give a luxury car 600 miles of range can give a budget car 250 miles of range at a third of the production cost. What makes this genuinely unique, not just a tiny upgrade, but a whole new ballgame, is a vehicle layout where the power supply and the physical body are one single entity, boosting each other's performance simply by combining mass and shapes. This isn't a small step forward. It's an entirely new class of solution. The brilliant minds behind this platform delivered a powerful tool. Whether global markets adopt it fast enough is up to politicians, investors, and automakers, not just the scientists. It's a brand new era. When you completely change how a car holds its power, every single component designed around that space changes along with it. Suspension tuning, crash barriers, heating systems, factory logistics, insurance metrics, mechanic training, and recycling pipelines all have to be completely rewritten. That massive shift will cause plenty of headaches in the short term, but it opens the door to incredible ideas that were completely impossible under the old rules. If changing how a vehicle physically holds its energy makes you wonder about the actual chemistry inside those cells, and what happens when the minerals inside those blades evolve as radically as the frame itself, that is a story you absolutely need to hear. And it happens to be the exact focus of our next deep dive. A brand new sodium battery technology is about to disrupt the electric car market forever. You can find that video link right below in the description. If this breakdown completely flipped your perspective on how electric cars are engineered, hit that like button and subscribe so you never miss our upcoming videos. Make sure to turn on notifications because we drop new content every single week. Now I want to hear your thoughts down in the comments. Is this integrated floor design a true engineering revolution that will define the next decade of transportation? Or is it just a manufacturing trick that only works at a massive scale?